Let's see how do we deal with that. This is the way those angles are might throw you off when you're dealing with this problem. So the uniform stone, let me see the following statement. The uniform stone supposed to be stone has a mass of 50 kilograms and is held in the horizontal place using a wedge at B, using a wedge at point B, right? If the coefficient, well, we have friction between the stone and so, okay, so if the coefficient of static friction at the surface of static friction at the surface of, let's say, the concrete, and the surface of the concrete is mu s is 0.3, right? Determine the minimum force P needed to remove the wedge. Assume that the stone does not slip. It's important. At A, there is no slipping there. Meaning that the friction between the stone and the concrete surface at point A is enough, is enough to make sure that this stone does not start moving when you're pulling this wedge. Right, that's an important phrase that has to be there. Otherwise, what if you're pulling this wedge and the friction between the wedge and the stone is too much that actually the stone starts coming with the wedge and start slipping on the surface at point A, right? So this is important. You can think about it as like this surface I'm talking about, right? This is when you pull this wedge P, this stone, and this stone is not gonna start sliding on the surface here. All right, it's just gonna, the friction, static friction would be enough to keep it there during this, whatever is happening. We're pulling this wedge out. All right, so let's take a look at free body diagram. All right, see what we have, what we don't have, and how can we deal with this. Well, we have to draw the free body diagram for the stone and for the wedge and look at both of them and see how can we actually find this force P, minimum force P. So I'm going to draw the free body diagram. Let's start with the stone. Let's see what we have. Well, we have the weight of the stone is 50 kilograms. It says it's uniform, meaning that center of gravity is exactly in the center here. So I can just put the weight there. Right, there you go. Exactly in the center. So that is, that means that this is like 0.5 meter. This is also 0.5 meter. This is 50 kilograms, so it's 50 times 9.81. That's weight. Now we have stone in contact with, we're isolating this. Don't get lost there, right? This is, we're isolating this to draw the free body diagram. Well, there is normal force between the surface and the stone at point A. Right? There's some normal force there. Call this NA, normal force at point A. Now, if this stone is supposed to move, if it moves, it doesn't. It tells us that stone doesn't slip. So this, whatever the friction is, it doesn't reach static friction, the maximum amount of possible amount for friction. It doesn't reach that. But we know if it does, the possible motion would be to the right for the stone. So the friction should be to the left. I put friction here to the left. Where does this normal force, where does it apply? Where should we put it? We don't actually know. All right, that's not, this is surface to surface kind of, this much surface here. So unless we make an assumption later on, we don't really know that. So this is friction at A. You can think about it as FA. All right. All right. Now, going to the right, the contact between the stone and the wedge. There is friction there, obviously. Remember, this is tricky. The normal force, there is a normal force between the stone and the wedge. Normal force is applied to the point of contact between two objects, right? Two rigid bodies or two objects, perpendicular to the surface of contact. So that means this is going to be my N. We can draw it here. There you go. This is going to be my N, NB. Right. This NB is I really exaggerated that. Maybe I could make it less exaggerated, more close to reality. This NB is still exaggerated, but otherwise we can't see. NB, this angle right here, this is 7 degrees. 7 degrees coming from this value right there. 7 degrees. This is 7 degrees. So if this is 7 degrees, the angle this creates with vertical direction is 7 degrees. Right? As NB applied to point B, perpendicular to this contact surface between the stone and the wedge. Then we have, I won't put the friction there yet. Let's go to the wedge. There is also friction force there, but let's go to the wedge because we have to detect or identify the direction for the friction from the wedge. All right, let's draw the free body diagram. I'm gonna make it larger here. So we have force P applied this direction. That NB I put on the stone should also be here in the opposite. This is NB. Just want to practice drawing free body diagram. So since P is pulling the wedge to the right, we have two sets of friction. One applied between the wedge and the surface, and one applied between the wedge is there between the wedge and the stone. So these are my friction forces. One is here, one is here, and both of them are parallel to surface. Direction is decided based on whatever is the direction of the possible motion. Possible motion is to the right. So these are my frictions. Right? That would be, let's call this F C, and then call this F B. Now that I know the friction between the wedge and the stone on the wedge, I'll go to the stone and put it in the opposite direction. Same friction should be there in the opposite direction. That's FB. Now remember, this angle here, 7 degrees. This angle here, 7 degrees. Right? So far, so good. Any question about this? All right. Minimum force P needed to remove the wedge, meaning that the minimum force you need to overcome friction. What is the minimum force that you need to overcome the friction? Generally speaking. What state are we if you're applying the minimum force to overcome friction?
Impending motion.
Exactly. Impending motion. If we apply more force, right, it's just going to start moving. So the minimum you need to remove this wedge is the amount of force that you need to overcome static friction, which means you're in impending motion. What does that mean? We should also put the normal forces here, right? We have one normal force from the floor. Also, this normal force is missing. This is N, called NC. So I'm just laying out everything, right? Then we'll figure out how to use this. Just make sure that you know how to draw free body diagram, deal with this. So look at this. That means FC would be mu S NC, and mu S is 0.3 NC. We are in impending motion, right? FB is mu S NB. Normal force on that surface plus coefficient of static friction, 0.3 NB. Oh, just these two. All right. All right. And we don't know FA, the friction between the stone and surface A, because that's not an impending motion. We said assume that the stone does not slip at A, meaning that on that side, we don't really reach the impending motion. So static is friction is unknown. Now let's see what we can do here. We are trying to find P. Right? Now P is on the wedge. Looking at that, so 7 degrees. Looking at that, if I let me also put the points so I can refer to them. This is A, this is B. It's pretty much it. If I write the equations in X direction, let's say for a wedge, let's see what we get there. Let's say for a wedge. Summation of forces in X direction is equal to 0. Positive, let's take this. So that will be P minus NB sine 7 degrees, right? and no, it's positive, and then minus the friction we have there, 0.3, and C is equal to 0. Did I miss? No, I missed. All right, let me do it again. P is to the right positive, FC is to the left negative, so minus FC would be 0.3 NC. Then we have N has a component is positive plus NB sine 7 degrees, and then we have FB to negative, so minus FB is 0.3 NB cosine 7 degrees is equal to 0. So many forces there. P is to the right positive, FC is to the left negative, FC is 0.3 NC, right? I just basically plugged in here FC. And this is FB. NB sine 7 degrees, NB is there. The X component is to the left, so negative. Sorry, X component is to the right, so positive, and FB is to negative, creates an angle of 7 degrees with the horizon, so that's going to be FB cosine 7 degrees, and negative to the left. Yeah. Summation of forces in y direction, take upward as positive. We have NC upward positive. We have minus NB cosine 7 degrees downward, and then that we have that FB there, so minus 3 NB sine 7 degrees, right, is equal to 0. This is just FB. I just plugged in. Let's see what we have and what we don't have. So we don't know what P is. We're looking for P. We don't know NC and we don't know NB. Right? NC, NB. So, a lot of unknown. We have 3 unknowns, 2 equations. We have a problem. We have a problem. We have to write another equation. Now, we can write the equation for the moment, but if you look at the wedge, we don't know where NC is applied. Right? If I want to write the equation for a moment about any point, I have to make this assumption that, okay, let's say NC is applied to some distance X, and then find the moment about some point. But here is the problem. Then the new equation is going to give me an equation, if I write the equation for moments about a point, but also is going to be an extra unknown. So I'm going to get an extra equation with an extra unknown. Doesn't help that much, right? But I can't use the free body diagram for the stone. Now I told you that this is a surface, but in this problem we're going to assume that it's just a point. That's how this they solved this. The way they did it, they said, as I said, we'll go further and I'll tell you. This is an assumption that typically you shouldn't make, but in this case, they're assuming that this edge is very on the edge, so we can say that the normal force is applied exactly at point A, that 1 meter distance from A to B. So it's not the typical kind of assumption, but in this example, they assume that the contact between the stone, which is not clearly specified, the contact between the stone and the surface at point A is just a point contact. So we know exactly where NA is. NA is exactly at point A. All right. So if that's the assumption they make, right? So it is assumed that stone is the only contact between the stone and the surface at and the left surface is at point A, right? If it was a surface-to-surface contact, we didn't even know where that is. But for the sake of argument, this problem says it's a point contact. So you know exactly where NA is. If that's true, if you make the assumption or you're told specifically, that means you can write the moment for the stone, right? For the stone block, you can actually write the moment about point A. If you do it, FA is gone, friction that you don't know. NA will be gone. Only things left are the weight FB, which is mu s NB, and NB in orange. So think about it. You write the moment about point A, and you get an equation as equation that only has NB as unknown. Okay, I'm going to repeat. If you write the equations for the moments about point A for the block, stone block, NA is gone and FA is gone. You get an equation that only contains MB. And you can find NB from there. And if you find NB, you can come back to the first two equations you wrote for the wedge. If you know NB, then you're going to have two equations, two unknowns, and you can solve this. So let's find the moments about point A. W is the weight multiplied by the distance, and it's clockwise, so that would be negative. So minus 50 times 9.81 times 0.5. NB, principle of moments, instead of finding the distance, perpendicular distance between NB and point A, right, which can be difficult, we're going to decompose NB to NB in X direction, NB in Y direction. X component of NB is passing through point A, so it doesn't create any moment. The Y component of NB is 1 meter away. The distance between Y component for NB is 1 meter from point A. Okay, so NB, two components. The X component passes through A, so no moment about A. Y component, the perpendicular distance between Y component and point A is 1 meter. So plus, and it's in clockwise. So NB cosine 7 degrees times 1. NB cosine 7 degrees times distance 1. And then we have the friction, right? This FB, which is mu s NB, and mu s is 0.3. So 0.3 NB. This one also, you decompose the component in X and Y direction. You are going to get NB, 0.3 NB, which is FB. FB sine 7 degrees, because that's the component that matters. Cosine 1 passes through point A. Right? Cosine passes through point A. Sine will be vertical. So again, 0.3 NB or FB in times sine 7 degrees would be the vertical component. And the distance of the vertical component from point A is 1 meter. So this becomes plus 0.3 NB sine 7 degrees times 1. This is FB in Y direction. This is NB in Y direction. It makes it easier to follow later. Is equal to 0. So in this equation, the only unknown is NB. You know everything else. Cosine 7 is obvious. Everything is just put as numbers. So NB becomes 230, 2383.1 newtons. Once you get NB, now your life is much easier. This is equation 1, equation 2. From 2, you can find NC. From once you know NC, from 1, knowing NC and NB, you can find P. So from 1 and 2, you can find NC and P. Okay. NC becomes NC, I found 2452.5 newtons, and P is 1154.9. Right, this is your P.